let's suppose we have a flat surface here, right? So let's call this surface S. Let's say it's flat, right? So then everywhere it has the same unit normal vector, n. Right? So n, this is a constant unit normal vector. Right, so it's an orientation of S is what it is, but the point is it's a constant vector. It doesn't change as you move around the surface. All right, now let's say we have a vector field F. Right? So this is, again, a constant field on S. Right. This could also, by the way, this could also be like a disk or something. It's just something flat. Right? All right, and then let's give this some meaning. Let's say it's the velocity vector field of a fluid flowing through a pipe, and this S here is a cross-section of that pipe. Right? So for some reason we have like a square-shaped pipe. But anyway, so we take a cross-section of the pipe, and then we have some fluid flowing through that pipe, right? And let's say that the fluid has direction going this way all the time. Right? Or, you know, this could be any number of things, right? But it's something, in some sense, flowing through another thing, right? Then we could say the flux of F through S is, you know, it's F dot n times the area of S. Right? That's the total flux of this vector field through that surface. All right. Well, of course, not all surfaces are flat, and of course, not all vector fields that represent something moving are constant. So you could ask, well, if we have some surface which isn't flat, and some vector field which isn't constant, how do we find the flux of F across that surface? All right. Well, the idea is to kind of use this as the guiding picture. All right. So for a general S and F, right? So for some general surface and for some general vector field F, right? The flux of F across S is we integrate over the surface. We want to integrate this quantity, F dot n, and then we integrate it over the surface. So this kind of gives you, this here gives you kind of the flux at a point in some sense, right? And this integrates it over the surface. All right? So you could do, you know, the usual Riemann to create this guy, but we'll just leave it like this. This kind of gives the clear picture. All right? And then what we do is actually write this in another way. Right? We're going to write this as F dot. We're going to put the n in with the ds, and then we're going to rename that guy, right, as F dot ds, where the s now has a vector. Right? So ds vector is the unit normal vector ds. Right? So what's the point of that? Well, this gives us a way to actually compute this guy now, right? So the flux, which is F dot ds, well, remember what n is. So n will be some r u cross rv this shouldn't be s anymore. This should be d. So here, I know this, sorry, this is kind of a little out of order, but s is parameterized by r of uv, where uv is in d. Okay? So then, this is n. Let's put that in pink here. Right? So that's the orientation on the surface. Right, so remember, of course, here, when we have this n, that gives an orientation on that. All right? Okay. And then ds, well, actually, let's not close this parentheses yet. Then ds, well, that's just the magnitude of ru cross rv dA. Right? So that lets us cancel these two guys, and it gives us the way of computing flux as the double integral over the domain of the parameterization of f dot ru cross rv dA. Right? So you'll notice here something important. The orientation matters because of this. So let's use pink here. So this thing, this implies orientation matters. Right. So one way you can kind of conceptualize or conceptually see that, imagine the surface, right? Then it has a distinct sort of inside and outside, and what tells you what's inside and outside is the orientation. So you kind of want to choose the correct orientation, the positive one, to know, like, is this thing flowing out of that closed surface, or is it flowing into it, according to whether the flux integral is positive or negative. Right? If you choose the wrong orientation, lines will kind of be backwards for that. Right? So this is the definition of flux. It's not too bad of an integral to compute. The definition is a bit messy. There's a lot built into it. But at the end of the day, it's really not so bad. You just have to be able to parameterize the surface, and then you get something that I think is even easier than computing the scalar surface integral. Right? And that reminds me, there's another name for the flux integral. So we can call this a flux integral. Or we can call it the vector surface integral of f over s. So I'll skip writing it because I think flux is just the better term for this, but that's another term you may hear. All right, so in the next video we'll do an example